Okay, so let's do this just like we've done the previous two videos. Let's make a little bit of a sidestep. Well, instead of thinking about things growing, let's think about things decreasing. And there's a number of different things that might decrease over time. What if one of those things was the value of something? So that every single year, whatever I purchased and its value went down 10% every single year. So we'll start with this, and the numbers are going to get ugly quickly. So here's a $1,000 item that I purchased. 1 year later, it would lose 10% of its value. And I chose this number on purpose because 10% might be easy to figure out, and that would be $100. That means that my new value is $900. Again, I would take 10% of this. And instead of going down like it did in the first year by 100, it's still going to keep decreasing, but at 10% again, now it's going to be worth $90 less than before, giving me $810. Now is where the numbers start to get kind of strange, because 10% of that is 81, ... But what this means is that I'm not really just taking 10% as I go down here. It's really like I'm taking 90%, which as a decimal is a fraction between 0 and 1. And then from here to here, I'm again going down by 90%. So it's like I have that starting number of 1,000, and I'm multiplying it by 9/10. And then my result, I am again multiplying by 9/10. And that result by 9/10 for a long time. And so rather than writing it all crazy complicated like that, I know that this is the same as multiplying it a repeated number of times. So my exponent is going to be attached to this number, and I'm going to be good to go. But usually these problems don't give you something where it says it's 90% of the value. So instead of dealing with that, you're going to have to do 1 minus that 10%, or in this case, 1 minus r. But really you don't know how much you're beginning with, like I did in this problem, so that's going to depend on some initial value, c. So if you want to find the final amount of something, this is the formula, and hopefully that helped explain it. Let's tag this formula first, and then deal with the reading of this part later. Y is going to be the final amount. C will be the initial amount. R is going to be the percent decrease as a decimal. I'm not going to write that all out. I'm just going to write the word rate, because I think by this point that hopefully is clear. And then for T, that's going to have to be in years. And if you're really flexible, you could make this work for months and things like that too. So let's read through the explanation of that. The general equation for exponential decay. The general equation for exponential growth. My fault. Please make sure that that says decay. The general equation for exponential decay is y equals c times the quantity 1 minus r to the power of t, where y represents the final amount, c the initial amount, and r represents the rate of change expressed as a decimal, and t represents time. So as we look at the label and the name for these notes, now we are no longer dealing just with growth. We're figuring out what that other part of the chapter title means, the section title, and that's decay. So as opposed to something getting larger over time, it's going to actually be getting smaller, and that should explain the subtraction part of the formula. So let's rewrite the formula as many times as is necessary, meaning I still want to do that for every problem because it's laying out the framework for me to plug these values in at, and it's also extra practice to memorize these for test. A fully inflated raft loses 6.6% of its air every day. Maybe before you even move on, you change that to a decimal by moving the place twice over, 0.66. The raft originally contains 4,500 cubic inches of air. That word originally is a hint that we're supposed to call and consider that our initial value. So that when I go through and I write an equation to represent the loss of error, I have 400 times the quantity 1 minus 0.066 to the power of t. And then if I simplify this, I would say 4,500 times the quantity 0.934 to the power of t. I'm looking at that to make sure I didn't subtract incorrectly in my head. The next part is the actual application of it, where they want you to estimate the amount of air that will be lost after 7 days. So already you can see that this works totally fine for something other than years, where I'm just substituting in 7 days, and then I reread through the problem just to be thorough. A fully inflated raft loses blah 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 of its air every day. Okay, cool. So the unit of time that they're asking me about matches the unit of time I was given in the problem. And when I type this into my calculator and I round up, I get 2,790 cubic inches of air. Alright, my problem is clearly labeled. I've shown all my work, and I scanned through it to make sure that this is reasonable. Well, if I start it with something and it's going to deflate over time, then I should get a smaller result. During the past several years, the population of Campbell County, Kentucky, has been decreasing at an average rate of about 0.3% per year. Ugly. Because it's ugly, maybe I take my calculator and divide that number by 100, or I actually show my work more thoroughly, so that when I convert this, I have 2 zeros in this problem before the decimal. And that would actually be what 0.3% is as a decimal. And no matter how you think about it, it makes sense. That's in the thousands place, and that would actually agree with being out of 100% and having to go back 1. In 2000, its population was 88,647. Same deal as before. Rewrite the formula, no matter how practiced you get with these. I'm not even thinking about choosing the formula because this is under the decay section, but on a test I would have to say to myself, is this going to be decreasing? And then I'd look here, and then I'd be like, well, that's the subtraction one, because I know it has to get smaller over time. I'm going to plug in I'm going to plug in the values. In 2000, its population was 88,647. That's going to be the start. And then I'm going to have 1 minus 0.003. Close that parentheses and get the exponent. Simplify this so that we don't have 1 minus showing up. And I'll get 0.997 to the power of t. You may look in your textbook and see that they show this or that. I think either one is pretty darn acceptable. Now we're going to have to use this. If the trend continues, predict the population in 2010. So I'm going to jump back, pulling out 88,647, and then I'm going to write my 0.997, and now I have to decide how much time has passed. Well, they're asking me about 2010, so this one's a little bit more straightforward than the other ones, where I'm going to use an exponent of 10 here. Maybe before you even do this, where will your solution be? End up being smaller, and it should. So I'm going to type this on my calculator, 88647 times the quantity, 0.997 raised to the power of 10. And once I round this one, I got 86,023.2 people. So I'll just write P-E-O-P-L-E. Now that's not a dramatic reduction. Well, that makes sense to me if I think about the fact that it is a 0.3% decrease. That's not wild. It's not like there was like some sudden craze to exit the town. Here's going to be the assignment that I want you to do over growth and decay. And I'm going to say, a couple of things. Growth. If you think about this, cancers all kinds of things grow exponentially. Money. So of all the math that we've done, this might actually be some of the most real-world math you'll come across. Decay. This is how people predict the, age of certain things and the time that they've been around. Like, they can actually look at elements and see how much they've decayed, and they can consider rewinding the clock back to say, well, that's when the dinosaurs were around. And also, if you think about something like blood alcohol content, this is how police officers know if somebody was drunk at the scene of a crime or at the time something happened. They can actually look at exponential functions and work their way back to figure out that when this guy ran that stop sign, even though they took his blood alcohol level here, they could go back and be like, well, that guy must have been absolutely drunk, and prosecute people based on this math-based evidence. So I think that's pretty cool to think about those applications of this stuff. Alright, this is definitely the kinds of notes you want to be confident on. So please seek me out, as I said, in every single video for this section.